In our video today, I will discuss all the types of stresses that we will cover in mechanics of deformable bodies, but I will just separate the three major types of stresses, and then for now, we will focus on the first type of stress. Now, the first type of stress is the axial stress, or it may also be called the normal stress, which will occur to members that are axially loaded, and then our axial forces can be tension or compression, and the force is applied at the cross-section of the member. Now, the equilibrium analysis of a rigid body is concerned primarily with the calculation of external reactions, which are forces that act external to a body, and also internal reactions, or forces that act at internal connections. However, in mechanics of materials, we must extend this analysis to determine internal forces, that is, forces that act on cross-sections that are internal to the body itself. In addition, we must investigate the manner in which these internal forces are distributed within the body. Only after these computations have been made can the design engineer select the proper dimensions for a member and select the material from which the member should be fabricated. Up to this point, we have been concerned only with the resultant of the internal force system. However, in design, the manner in which the internal forces are distributed is equally important. This consideration leads us to introduce the force intensity at a point which is called stress, which plays a central role in the design of load-bearing members. Through statics, we are able to perform the first step in the analysis of a given structure. However, they do not tell us whether the given load can be safely supported. The strength of a certain member depends upon the value found of the internal force and also upon the cross-sectional area of the rod and the material of which the rod is made. As such, the internal force represents the resultant of elementary forces distributed over the entire area, and the average intensity of these distributed forces is equal to the force per unit area. Whether or not the members will break under a given loading clearly depends upon the ability of a material to withstand the corresponding value of the intensity of the distributed internal forces, and thus it depends upon the force, the cross-sectional area, and the material of the rod, which will give us an idea of the allowable stress. Now, the force per unit area, or intensity of the forces distributed over a given section, is called the stress on that section, and it is denoted by the Greek letter S, which is sigma. And so the stress in a member of cross-sectional area A, subjected to an axial load P, is therefore obtained by dividing the magnitude of the force P by the cross-sectional area. Again, axial stress is a type of stress that occurs when a force is applied along the axis or length of a structural member, such as a beam, rod, or column. It represents the internal force per unit area acting on a section of the material perpendicular to the applied force. The axial stress can be either tensile or compressive, depending on the direction of the applied force relative to the material. Tensile stress is a type of axial stress that occurs when the force applied to a material tends to pull it apart or elongate it. In other words, tensile stress develops when a material is subjected to stretching or pulling forces. And then tensile stresses are considered positive because it leads to elongation along the axis of the applied force. And then on the other hand, compressive stress is another type of axial stress that occurs when the force applied to a material tends to push it together or compress it. Compressive stress develops when a material is subjected to squeezing or pushing forces. And then it is considered negative because it tends to decrease the length of the material along the axis of the applied force. Now, for both of these stresses, the area of interest is the perpendicular area. Now, let's try to consider the objects shown subjected to a force P. And then let's recall the definition of the word perpendicular. Perpendicular is a geometric term used to describe the relationship between two lines, planes, or surfaces that meet or intersect at a right angle, which is 90 degrees. In simpler terms, if two lines, planes, or surfaces are perpendicular to each other, they form a right angle where they intersect. If you look at our force P, notice that it is perpendicular with this line, this one, and this one, because this is a 90-degree angle, and therefore, it is perpendicular. Therefore, our perpendicular area will be these areas. However, in our exams, we may not be able to make sense of the area that we will consider since we usually only view our bodies in 2D. But note that the area we are considering here is the cross-sectional area. Now, the cross-sectional area refers to the area of a two-dimensional shape that results from cutting or slicing through a solid object perpendicular to its longest dimension or axis. In simpler terms, it is the area of the shape that is revealed when you make a straight cut through an object such as a cylinder, cube, or beam at a right angle to its length. Now, if we'll rotate our body, we will be able to see that area. And so rotating these, we have this figure. Now, for a cylindrical object like a pipe or wire, the cross-sectional area would be the circular area that you would see if you cut the cylinder perpendicular to its axis. And then for rectangular objects, such as this one, the cross-sectional area would be the rectangular area that you would see if you cut the cube perpendicular to its length. Now, in some cases, our cables or rods may be inclined, but we will still consider a force perpendicular to that area, which is essentially the compressive or tensile force in a member. Now this P right here, this one and this one, they are the resultant forces in our members, or simply the internal force developed in our members. However, if we will get the stress or pressure, we will now be distributing the resultant force P over the whole area. And so instead of this, we will now distribute the force this way. And so notice that the force has been distributed throughout the cross-section. In general, the value obtained for the stress sigma at a given point Q of the section is different from the value of the average stress given by the formula P over A. And then sigma is actually found to vary across the section. The actual distribution of stresses in any given section is statically indeterminate. However, in practice, it will be assumed that the distribution of normal stresses in an axially loaded member is uniform, except in the immediate vicinity of the points of application of the loads. The values of the stress is then made equal to save time, and then we can obtain it from the formula, which is force over area. However, we should realize that when we assume a uniform distribution of stresses in the section, such as when we assume that the internal forces are uniformly distributed across the section, it follows from elementary statics that the resultant P of the internal forces must be applied at the centroid C of the section, which is for the rod right here and then for the cube at this point. This means that a uniform distribution of stress is possible only if the line of action of the concentrated loads passes through the centroid of the section considered. Now, since SI metric units are used in this discussion, with P expressed in newtons and A in square meters, the stress sigma will be expressed in Newton per m squared, and then this unit is called a Pascal. Now, let's write that here. 1 Pascal is equivalent to Newton per m squared, and so if we have kPa, that will just be Kn per m squared, and then if we have MPa, that will be meganewton per m squared, and then if we have 1 GPa, that will be giganewton per m squared. As such, 1 kPa is equal to 1000 Pa, and then 1 MPa is equal to 1000 kPa, and then 1 GPa is equal to 1000 MPa. This will be our conversion. Now, in our usual calculations, we will be using the MPa unit because our cross-sections are usually small and have dimensions in millimeters. However, although MPa is meganewtons per meter squared, we can just automatically convert that to Newton per mm squared. And so this is just Newton per mm squared. And so let's try to prove that. We know that 1 Kn is equal to 1000 newtons, and then 1 meganewton is equal to 1000 Kn. And so let's use these conversion factors. And so for MPa, we have Mn per m squared. So this is Mn divided by m squared. And so let's try to convert Mn into newtons. And so writing that here, 1 Mn is equal to 1000 kilonewtons. So this is 1000 Kn. And then 1 kilonewton is equal to 1000 newtons. And so this will cancel, and also this one. So we are left with newtons. And then for m squared, we want to convert that to mm squared. And so we know that 1 meter is equivalent to 1000 mm. However, since this is squared, we will also square this one. And so essentially we have 1000 times 1000 and then times newtons, because that will be the unit that will be left, divided by m squared will cancel, because if we will square m, that will just be m squared. And so our denominator will be 1000 mm and then squared. And so notice that this is also 1000 squared. And so these will just cancel, and then we are left with Newton per mm squared. And so notice that our conversion factor is just 1, because all of the values will just cancel. And so that's why we can say that n per mm squared is just equal to mn divided by m squared, or 1 MPa. And so this is how we are going to go about that. Now, let's try to solve this problem involving axial stresses. We have a hollow steel tube with an inside diameter of 100 mm, and then it must carry a tensile load of 400 Kn. And then we have to determine the outside diameter of the tube if the stress is limited to 120 Mn per m squared. Now, if you look at our figure in 2D, this is the side view of our system. This is our hollow steel tube, and then we are applying a tensile force P, which is acting away from our body. Now again, in axial stress, our area of interest is the perpendicular area, and then if we have this vertical force P, this line is perpendicular to that. And so we are interested in the cross-sectional area. And so if we'll rotate our figure to see the cross-sectional area, it will look like this. This is our cross-sectional area. Now, the inside diameter of our tube is 100 mm, and so it will be this dimension. This is 100 mm. And then what's required in our problem is the outside diameter, which is this one. Let's project a line here. This is our outside diameter. Now looking at this, our cross-sectional area will be the area of the larger circle, which is this one, minus the area of the inside circle. Because remember that this is a hollow section, and so this area is just essentially a hole. And so our area will be the area of the outside circle minus the area of the inside circle. Now, the area of a circle has two formulas. We have, in terms of the radius, that will be pi r squared. And then in terms of the diameter, we have pi d squared divided by 4. Now, you may use any of these. However, since the problem asks the diameter, let's just use this formula. Now recall that stress is equal to force over area. Our stress is limited to 120 mn per m squared. And so recall that this is just MPa because we have meganewtons. And then also recall that MPa is just equal to Newton per mm squared, as we have discussed earlier. And then our force P, which is our tensile force, that's 400 kN. And so we have 400 kN. And so plugging in our values, we have stress equals force over area. Our sigma is 120 MPa, or Newton per mm squared. And then that's equal to P, which is 400 kN, divided by the area, which is the area of the outside circle minus the inside circle. And so our area will be, the outside circle is pi d squared over 4, which corresponds to this one. And then minus the hollow portion, which is pi times the diameter is 100 mm, and then squared divided by 4. However, notice that our force P is in kilonewtons, but we need to be consistent with our units, and so we will convert that into newtons by multiplying it by 1000. And so we have 1 kN is equal to 1000 newtons. And so now we will be able to solve D. Let's just use our calculators. So that will be 120 is equal to 400 times 1000 divided by pi times d squared over 4. Again, this is our unknown. And then minus pi times 100 squared divided by 4. And so press shift solve, we can get our diameter, which is 119.35. And so this is 119.35. However, in reality, there are no available sections that have this actual dimension. And so we'll round up to, let's say, 120 mm. Now again, when asked for the area or dimension, always round up, because having a larger area will reduce the stress in the member and it will ensure safety. And so this is our answer. Now, let's try to deal with problems that will refresh our knowledge in statics, because in most cases, we will be solving the internal forces in our members, which will be obtained from our equilibrium equations. Now, for our first problem, we have a uniform 300 lb bar AB, which carries a 500 lb vertical force at A. Now, lb just means pounds. Now, the question that will arise is, where will the weight act? Take note that the weight acts at the centroid of the member, and so it will be somewhere here. And then we have a 500 pound force at A. And then let's not forget the external reaction at B, which is a hinge connection. Now, the diameter of our member CD is 0.5 inches. And then because we are to find the stress in the cable, we need to find first the internal force developed in the cable. And so drawing our triangle, we have these components. And then we essentially have a 3-4-5 triangle. Now, because the tension in CD is inclined, we have vertical and horizontal components. And then let's label that CDY and CDX. And then to get CD, we can take moments about B, because we know that we have external reactions at that point. And so we will do that to exclude them. And so taking moments about B, we have negative 500 times the perpendicular distance, which is 6, and then minus 300 times 3, and then plus CDY times 3, and then that's equal to 0. And so simplifying that, we have this equation, and then we can now get CD. Using our calculators, we will be able to know that CD is equal to 1625 pounds. However, if you don't want to simplify the equation, you can just use shift solve, and then you will still be able to obtain the answer. However, take note that we are not in statics anymore. We are not only interested in the force in the member, we are now also interested in the stress. And so this is just the first step in our calculation. Now, to find the stress in the cable, we will just simply divide the force by the area of the cross-section. Now, the diameter of the cable is given, and it is 0.5 inches. And so we'll use that in our calculation. And then the formula we are using here is the area of a circular section. Now, our resulting unit is lb per inches squared, which is just equivalent to psi, because this means pounds per square inch. And so this is our answer. Now, in our next problem, we have to find the stresses in members BC, BD, and CF for the truss shown. And then we have to indicate tension or compression. And then we are given the area, which is 1400 mm squared. And so let's just color our members. Again, our cross-sectional area is 1400 mm squared. And then we have to find the stress. And so this is what we need. Now, to solve the internal forces, we can use the method of sections to avoid solving the external reactions. Because our truss figure has 4 unknowns, because we have 2 hinges. And so this is essentially indeterminate. However, we can also use the method of joints in conjunction with the method of sections. However, we will start from left to right. To vary our solutions, let's use the method of joints to solve the force in BC. Notice here that the method of section is not ideal for this member. Now, let's first isolate joint A, and then we'll sum up vertical and horizontal forces. Next, we can use our calculators to solve the equation simultaneously, so that we can find the force in AB and AC. Now, if we try to look at the components of AB, we have a 3 meter horizontal distance and a 3 meter vertical distance. And so since the legs are equal, that will just be a 45-degree triangle. However, if we are to check using the arctangent function, we can use arctangent and then 3 divided by 3, which is opposite over adjacent, which will give us 45 degrees. First, we can sum up forces horizontal. And so we have AB cos 45 and then plus AC. And then since we don't have any horizontal external forces, that will just be equal to 0. And then summing up forces vertical, we have AB sine 45 minus 40 is equal to 0. And then if we'll simplify that, that will be AB sine 45 is equal to 40. And so using our calculators, we can treat this as our equation 1 and equation 2. And so solving that simultaneously, we have this one. And so our AB will be 56.569, and then our AC will be 40. And then AB is in tension, and then AC is in compression, because we are considering the signs. Again, positive corresponds to tension, and then negative corresponds to compression. Again, the first member that we will consider is member BC. And so we will actually move to joint B in order to solve BC. And so isolating joint B, we have this figure. And then if we'll write our ratios, we have for AB an angle equal to 45 degrees, which is what we solved earlier. And then for BD, we actually have a 3-4-5 triangle. And so given that the analysis of trusses was already discussed, we will just fast forward the solution. And then we'll just use our calculators to solve the equation simultaneously. Now, summing up forces along X, we have minus AB cos 45 and then plus BD times 4 over 5. And then that's equal to 0. However, we know that AB is equal to 56.569. And so we'll substitute that into our equation. and thus we can find BD, which is 50 kilonewtons, and then tension, because our result is positive. Now, summing up forces vertical, we have the vertical component of AB, which is going down, and so that's minus AB sine 45, and then minus BC, which is just a vertical component, and then minus BD times 3 over 5, because we need the vertical component, and then it's going down, and so that's why it's minus. And then all of that will be equal to 0. However, we know that AB is equal to 56.569, and then BD is equal to 50, which is what we solved earlier. And so using those values, we can now solve BC, which is 70 kN, and then compression, because our result is negative. And so solving the stress in BC, we have 70 kN, and then times 1000 to convert that to newtons, divided by 1400 mm squared, which is 50 Newton per mm squared, which is just equal to MPa. And so this is essentially 50 MPa. Now, for the stress in BD, we will just use what we solved. We identified that BD is 50 kN and then tension. And so that's 50 kN times 1000 divided by 1400 mm squared, which is just 35.71 MPa. Now, finally, for the force in CF, I can use the method of sections. And then we can make this cut. And then let's take moments about D, so that we can eliminate CD and BD in our calculations. Remember, CF has components of 4 meters horizontal and 4 meters vertical. And so we know that it is a 45-degree triangle. However, just to differ our solutions, we will just use the components. The hypotenuse of the triangle will be 4 times square root of 2. However, we will just divide all of the sides by 4 to reduce our ratio. And so we have 1 and 1 for the sides, and then square root of 2 as the hypotenuse. And so taking moments about D, we have minus 40 times 7, because it will cause a counterclockwise rotation about D, and then minus 70 times 4, and then minus CFY times 4, and then that's equal to 0. However, we know that CFY is just CF times 1, which is the vertical component, divided by the hypotenuse, which is square root of 2. And so solving CF, we have negative 197.99 kN. And then that's compression, because our result is negative. And so the stress in CF will be 197.99 times 1000 divided by 1400 mm squared, which is 141.42 MPa. And then that's in compression. Now, there's actually a more efficient way to get the force in BC, and that is using the method of sections. However, I just showed you the joint method earlier in order to explore the methods. However, if you are to use the method of sections, we can actually cut the member this way. And so now, we will be able to reveal the internal forces. Let's try to zoom in. This is AC, this is BC, and this is BD. And then we'll just consider the left side of the section. Now, if we'll extend the line of action of BD, it will hit point D. And then if we'll extend the line of action of AC, it will also hit point D. And so we can take moments about that point to get BC. Now recall that the force in BC is equal to 70 kN. And so if I will take moments about D, I have minus 40 times 7, and then minus BC times 4. And then this is equal to 0. Now take note that 70 kN is already excluded, because this is at the right side of the section. We will only consider these forces. And so solving BC, we have minus 40 times 7 minus x times 4. That's equal to 0. And so our BC will be minus 70, which means that it's in compression. So this is minus 70 and then kN compression, which is just the same as this one. Now, this was in tension earlier. There's something wrong with my solution. Let me try to check. Now, this is a snippet of the video. Now, I actually got it wrong right here, because this was negative 70 kN. And so this is supposed to be compression. And so let's just change this one. This is compression. And so take note of this correction. Now, in our next problem, we have a column that consists of a wooden post and a concrete footing, and they are separated by a steel bearing plate. And then we are to find the maximum safe value of the axial load P if the working stresses are 1000 psi for wood and 450 psi for concrete. Now, in this problem, we have two considerations. We have to solve P in terms of the wood, and then we have to solve another value of P in terms of the concrete, and then we are to choose which of those values will be safe. Our allowable stress for the wood is 1000 psi, and then for concrete, it's 450 psi. Now notice that if I make a cut at the wooden section, and then I will sum up forces vertical, then the internal force in the wooden member is actually just equal to P, because we don't have any other vertical forces. In the same way, if I cut at the concrete footing, and then I will sum up forces vertical, then the internal force in the concrete footing is just equal to P, because we still don't have any other vertical force. Thus, our formula will just be P divided by the area of the wooden post and the concrete footing, but we will separate the two. Now, considering the wooden post, we have an allowable stress of 1000 pounds per square inch, and then that will be equal to P divided by the area. Now, the area of the wooden post is actually circular, and so that will be pi times d squared divided by 4. And then the diameter of our wooden post is 8 inches, and so we will use that dimension. And so solving P, we have 50,265.48 pounds. This is the allowable load considering the wooden section. And then for the concrete footing, our allowable stress is 450 psi, and then we have P divided by the area, which is just essentially a square. And so that will be 12 inches and then squared. And so solving P, we have 64,800 pounds. Now, the next question that will arise is, which of these loads is safe? Now, we know that the larger the load, the greater the capacity of our member should be. And so that means that carrying a smaller load will be safe, because our members will not carry a lot. Notice that the concrete footing can carry 64,800 pounds. However, the wooden post can only carry 50,000 plus pounds. And so that means that our concrete footing has a greater capacity. However, we will always consider the weaker member, because that will govern the design of our structure. The next problem we have will deal with a little bit of statics and algebra. However, I will be showing you how you can solve this problem efficiently using a calculator technique. So, in this situation, we have to determine the largest weight W that can be supported by the two wires AB and AC. The allowable or working stresses are given, which is 100 MPa for AB and 150 MPa for AC. The cross-sectional areas also vary between the two wires. AB has a cross-sectional area of 400 mm squared, while AC has a cross-sectional area of 200 mm squared. Now, let's first resolve AB and AC into components. So for AB, we have vertical and horizontal components, which are ABY and ABX. And then for AC, we have ACY and ACX. Now, to solve this problem, we can just consider joint A, and then we'll sum up forces vertical and horizontal. Now, summing up forces horizontal, we have minus AB cos 30, because our component is going to the left, and then plus AC cos 45, and then that's equal to 0, because we don't have any horizontal external forces. And then summing up forces vertical, we have AB sine 30 plus AC sine 45, and then minus W, and then that's equal to 0. And then to simplify our calculation, we can just move W to the right so that it will be positive. And so we have AB sine 30 plus AC sine 45 is equal to W. Now, let's try to solve our problem using algebra. We want to express the tension in AB and the tension in AC in terms of W, so that we can plug it into our equation stress is equal to force over area, wherein our force is the tension in the wire. However, we must express that tension in terms of W to determine the largest weight W that a specific wire can carry, and then we'll check which of the forces is safe. Now, you can also solve this problem using the force triangle. However, I will discuss that in another video. In the first step, we will just move AB cos 30 to the right so that it will be positive. And then we will divide both sides by cos 45. And so our AC will become AB times cos 30 divided by cos 45. And then considering our second equation, which is summation of forces vertical, we can rewrite that. And so we have AB sine 30 plus AC. Now, let's change our AC because we already have AC in terms of AB. And so we will change AC into AB cos 30 divided by cos 45. And then don't forget that we are still multiplying that by sine 45. And then that's equal to W. Notice that our expression at the left side of the equation all contain AB. And so we can add all of the coefficients of AB such that we'll only have one coefficient. Using our calculators, we can input sine 30 and then plus cos 30 over cos 45 times sine 45. That will give us 1.366. And so 1.366 AB is equal to W. But remember that we want to express the tension in terms of W. And so we need to divide both sides by 1.366. Thus, AB will be W over 1.366, which is 0.732 W. Now that we have AB in terms of W, let's substitute this into AC so that we can also express it in terms of W. And so AC will be equal to AB, which is 0.732 W times cos 30 over cos 45. And so essentially, AC is 0.897 W. And then now, since we have expressed AB and AC in terms of W, we can now get the safe W for each of the wires. First, let's consider wire AB. We know that stress is equal to force over area. Now, the allowable stress in AB is 100 MPa, and then that's equal to force over area. Our force is the tension in AB, which is 0.732 W. And then we will divide that by the area of AB, which is 400 millimeters squared. Solving W, we can get 54644.81 newtons. And so this is the value of W that wire AB can carry at maximum. Next, let's consider wire AC. Again, stress is equal to force over area. The allowable stress in AC is 150 MPa, and then that's equal to force over area. But our force now is the tension in AC, which is 0.897 W. And then we'll divide that by the area of AC, which is 200 millimeters squared. Solving W, we can get 33,000.82 newtons. And so this is the value of W that wire AC can carry at maximum. And so, as discussed earlier, when the safe load is asked, we will pick the smaller load so that both of our wires will be capable of carrying the load. Now, for this item, you can actually get the coefficient of W just by using a calculator technique. Now, let's try to do that. And so, press mode, and then go to equation, and then pick two equations, two unknowns. And then we'll type here our coefficients of AB and AC. Now, our first equation is negative AB cos 30. And so this is minus cos 30. And then the coefficient of AC is cos 45. So this is cos 45. And then for the second equation, we have AB sine 30. So we have sine 30 and then plus sine 45. That's equal to W. However, note that W is still an unknown. However, if we want to express AB and AC in terms of W, then we can just treat this as 1. Because the concept here is that we are taking the ratio of the weight and the forces carried by AB and AC. And so if we'll treat that as 1, we are just essentially solving the force in AB and AC for every 1 kilonewton load. And so I hope that's clear. And so if we'll input 1 here, this will act as our W. And then if we press equals, our X will be 0.732. However, that's in terms of W. And so notice that this is the same with this one. And then if you press equals again, you will get Y. And then notice that this is also the same with this one. And so this is how you can obtain these values by using this calculator technique. And then the next part of the process will just be the same earlier, which is solving the safe load. Now, I already have a video explaining this last problem. However, the orientation was horizontal. In this one, we have an orientation wherein the axial loads are vertical. But there's no need to worry, because if you're used to the conventions of the horizontal orientation, you can just actually rotate this figure and then draw the axial force diagram. However, in this example, I will teach you the conventions when you have this orientation. On the basis that negative is compression and positive is tension, downward forces are acting toward the body, and so that's compression, whereas upward forces are acting away from our body, and so they will be deemed tension. Now, let's consider left as the negative side, while right as the positive side. In this configuration, we'll move left if we have downward forces, while we'll move right if we have upward forces. Now that we have made that clear, we will first solve the normal reaction at the bottom, because notice that our body is not in equilibrium. How do we know this? If you sum up vertical forces, they will not equal 0. Minus 2p plus p minus 4p is negative 5p, and thus we have a net compressive force. We need to counteract that through the normal reaction at the bottom. And so let's add our normal reaction and then let's sum up forces vertical. We have minus 2p plus p minus 4p plus n is equal to 0. Moving all terms containing p to the right, n is equal to 5p. And so this is our normal reaction. Now that our body is in equilibrium, we can already draw our axial force diagram. Again, we'll consider left as the negative side, while right as the positive side. Note that you can only apply the conventions discussed if you are going from top to bottom. And then for the horizontal orientation, you can only apply the conventions if you are going from left to right. Now you have to take note of this. And so considering the topmost part of the steel section, we have 2p moving downward. And so we'll move to the left. From the 0 line, we will move 2 units to the negative side. And so that will be minus 2p. And then, since there's no axial loading between the steel and timber section, we will draw a vertical line to indicate a constant value. However, at the top part of the timber section, we have a force P acting upward. And so from negative 2p, we'll move to the right 1 unit, because this is essentially 1p. And so minus 2p plus 1p, that will be minus 1p. And then let's draw another vertical line. Now, at the top part of the concrete section, we have 4p acting downward. And so we'll move again to the left. Now, minus 1p minus 4p will give us negative 5p. And then at this point, we will now draw another vertical line up to the bottom part of our figure. Now, remember that this system is in equilibrium, which means that for the axial force diagram, the axial force must start at 0 and end at 0. Now, we still have negative 5p here, but our normal reaction at the bottom will counteract that force, because our normal reaction is equal to 5p, which is acting upward. And so we'll move 5 units to the right, and we'll actually end at 0. Now, if you're drawing the axial force diagram and you will not end at 0, then that means that there's something wrong with either your drawing or your solution. That's how you can check. Now, what this diagram means is that the steel section carries a compressive force 2p because we have negative, and then the timber section carries a compressive force minus p, and then the concrete section carries a compressive force 5p. And so now, we will solve the individual values of p. First, we will consider the steel section. For steel, our allowable stress is 120 MPa, and then our cross-sectional area is 500 mm squared. And so using stress is equal to force over area, we have 120 MPa is equal to 2p, because that's carried by the steel, divided by the area, which is 500 mm squared. And so solving p, we have 30,000 newtons. Now, for timber, our allowable stress is 12 MPa, and then our cross-sectional area is 2000 mm squared. And so 12 MPa is equal to P divided by 2000 mm squared. And so solving P, we have 24,000 newtons. And then finally, for the concrete section, we have an allowable stress of 16 MPa, and then our cross-sectional area is 8000 mm squared. And so 16 MPa is equal to 5P, which is carried by the concrete, divided by 8,000 mm squared. And so solving P, we have 25,600 newtons. Now, since timber has the lowest value of P, it will govern our design. And so the maximum allowable value of P will be 24,000 newtons. This sums up everything you need to know about axial stresses. And so I hope this video helped you.